Professor Bialis here. In this video we're going to be talking about section 12.1 where we talk about the algebra of functions and then composition of functions. We're going to start with algebra of functions, but really it's more an arithmetic of functions. Let me show you what I mean. So let's say we have a function f of x equals x squared plus 3x minus 5 and g of x equals 4x plus 3. Okay? Well, let's use something different so you don't have the two 3's there. Let's say 4x plus 7. Okay? Now those are just two given functions. You don't have to worry about where they're coming from. They're just given to you. The algebra of functions talks about how we add, subtract, multiply, and divide different function values. So this is why I am calling it more an arithmetic of functions. But it's algebra because we're dealing with algebraic expressions. So let's say we have something like this. Okay? Now that is the function notation of the sum of these two functions. Sometimes we simply write it like that where there's no input listed. When that happens, it's understood to be that x. Another way we could write this, and this is kind of really showing what's happening, is when we have f of x plus g of x, like so. Don't think of this as distributing the x. It's just a different way of writing something. Nothing more than that. Okay? So when you see it like this, which is really saying what we're doing, all we're doing is taking one function and adding it to another. So it would come out like this. The function f plus the function g. And when you look at it like that, what are we doing? We're simply adding a trinomial and a binomial. So pretty much we're adding function. We're literally adding the expressions of the functions. So what we get is x squared. We can just ignore the parentheses here. So 3 plus 4 is 7x. Negative 5 plus 7 is 2. And that's it. Nothing more to it than that. Okay? So again, please do not overthink something like this. Now, what if we have g minus f? Something like that. Now we're subtracting. Remember, if there's no input listed, that's really understood to be that. And then you could think of it like so, where we literally are just taking the g expression, subtracting the f expression. So what that would turn into is 4x plus 7 minus x squared plus 3x minus 5. And when we see something like that, it's not just combined like terms. The first thing we would do is distribute that negative like so, and then we would combine like terms. So negative x squared, 4 minus 3 is just a single x, and then 7 plus 5 is 12. And there we go. Next one, how about multiplying? Let's say we have f times g. Again, that could be written as f times g of x. Then we can finish it off as f of x times g of x. Okay? Now, with that, we would simply, again, just go with x squared plus 3x minus 5 times 4x plus 7. Okay? And then we would just distribute. Okay, so when we distribute, you can think of distributing either right to left or left to right, whichever you are more comfortable with. So let's say we're doing left to right. So I would take this x squared, distribute it over these two first. So it would be 4x cubed plus 7x squared. Then I would take the 3x, distribute. And then I would take the negative 5, so negative 20x minus 35. Okay? After that, we would just combine those like terms and call it a day. So we have 4x cubed, and then we would have 7 plus 12 is 19 x squared. And then we would have 21 minus 20 is just a plus x, and then minus 35. Okay, and that looks good. So again, really all this is polynomial work. That's really all it is. It's just now we're calling them functions. Nothing more to it than that. Last thing about would be division. Let me come up here. So that would be f over g. Typically that's going to be presented to you as a fraction. Now what I would then do is, again, I can sometimes see it like this. You don't have to write it as those two. I'm just giving you the possibilities of what it would be given to you as. And then what that really means is f of x over g of x. Again, you don't have to write all three of those out. Those are just the possible presentations of that problem. So what we would have there then is x squared plus 3x minus 5 all over 4x plus 7. Now what I would want you to be doing there is, if it's possible, factor and simplify. But in this case it's not. Okay, that's the best you can do. One other thing that they do include in this is that they are going to ask you to also give any domain restrictions if applicable. So in this case, when you're introducing a fraction like this, that denominator needs to be restricted. So remember, that denominator cannot equal 0. So we need to know when that happens. So I'm going to subtract 7 and then divide by 4. And we get that. Now how we would list that is simply semicolon and then x is not equal to -7/4. And that whole thing would be your result. So that is something that is nothing new. It's old news from chapter 7, but it's something we have to remember to do. Whenever you introduce a fraction like this, you have to restrict that denominator. But as you can see, other than that, it's very straightforward. You're adding, subtracting, multiplying, or dividing polynomials. Okay, so please don't overthink any of this. Now, if let's say they gave you a question like this, let me clean this one up. Let's say they did f plus g of 2. There's a couple ways you can go about this. You could take that 2, plug it into the f function, get a value for that, plug it into the g, and then add those two numbers. Or if you have this algebra worked out already, you can just jump into this. Okay? So what we could do is simply take x squared plus 7x plus 2, plug in those 2's to get a 4 plus 14 plus 2, which is 18 plus 2, or 20. Okay? Now, again, if we wanted to, let's say we didn't have this worked out, what we could have done is take the 2 in for the f, that's 4 plus 6 is 10, minus 5 is 5, and then 8 plus 7 is 15, so 5 plus 15 would also give you the 20. Okay, what's nice about this is, let's say we knew that we had to plug in a bunch of values into this expression here. We could find that expression algebraically first, and then plug in as many values as we need. But if they say, you know, here are your two functions, find this, again, we do have the option to plug them right in, and then we don't have to do any combining like terms or anything like that. Okay, so that is the algebra of functions. Now let's go into composition of functions. I want to start by just showing you how it's done, and then we're going to talk about how to build compositions themselves. So let's keep the same f and g functions we started with, but now composition is going to be notated like this. Okay, now I want you to see the difference between this and this. If you glance at them, you can very easily mix those up. A very small closed dot is multiplication. This open dot is composition. Okay, so another way you could see this again is with that x clearly stated, or what's really happening here is that those all mean the same thing. Okay, now we would say this as f composed with g. Okay, now if you look at this last notation, this really tells you what's happening. You're basically doing one of those nesting dowels where you open up the top and there's a smaller dowel, open up the top, a smaller dowel. That's what's happening here. You take that input, plug it into G. That then calculates it out to a new output, which then gets plugged into F. Okay, so let's say I ask you for F of G of, let's say 2. Let's say 2 again. Let's say I do it like that. Now, again, just kind of the basic fundamental way of doing it, I plug a 2 into G. If I go find G of 2, that's 4 times 2 plus 7. That's 8 plus 7 is 15. What I then do is plug that into here. So this turns into F of 15. So inputs 2, G outputs a 15, which then gets input back into F. And then I would go about it this way. Okay, if you think back to that, I believe I did a baseball example when I introduced functions. A function basically takes a raw piece of, is like a machine in a factory. If I take a raw piece of wood, pump it in the machine, that raw piece of wood is my input, and then if it carves out a baseball bat, that's my output. Okay, what this is basically a two-phased machine. So if, let's say, I pump in a raw piece of wood, it cuts it to length, and then it takes that new length and carves out the baseball bat. Okay, so there's just a couple layers of function work going on. And then here what I would get is 225 plus 45 minus 5. So that is, I could just think of this as 40, so 265. And there we go. Now that's a very piecemealed, one step at a time way of going through that. Another way you could have done it, which is the way I personally like to do it, but again, that's a personal preference, is to build the entire thing at once. Okay? So what do I mean by that? If I have f of g of 2, I always work from the outside in. So I'm going to start with the function f. Now the function f is this whole thing here. So I have x squared plus 3x minus 5. Okay, then, use red here, I would plug g into that. So that would be 4x plus 7, 4x plus 7. And then ultimately, I would plug that too. Again, this is the same problem, this is just another way of doing it. This is, okay, find that calculation, plug it in, calculate again. This is just making one long algebraic or arithmetic expression that I need to work out. Okay, and when I do that, then what do I get? 4 times 2 is 8, plus 7 is 15. 15 again. And look at what happens. I get the exact same thing as I did here. It's just this is more of a, you start here, you work your way down, as opposed to go off to the side, figure that out, then plug it back in, then work your way down. Whichever way flows in your mind, I want you to stick with it. Okay? And then I get the 225 plus 45 and so on, and then that again is 265. So again, two different approaches, both are perfectly fine. You use whichever is better for you. Another reason I like this one is when I don't define a numerical input, this is a little easier to go through. Let me show you what I mean. Let's use a couple new functions here. Let's say f of x is 7x plus 2 and g of x is 3x minus 8. Okay? Let's say I ask you for this. Notice there's no numerical input that I'm going to get an answer like this. I want to keep it all algebraic. So again, I could think of this with an input of x, or if it helps, I could rewrite this like so. Okay? So I'm starting with f. I have that all-encompassing f, which is 7x plus 2. There's my function f. Inside that then goes that g of x, which is 3x minus 8. Okay? And then I just work through that way. So I get 21x minus 56 plus 2. 21x minus 54, and there's my answer. Okay? Again, there was nothing to plug in. If I wanted to do it always where I take that g of 2 and I plug it back, that's fine numerically, but if you're doing this algebraically, we need to keep the frameworks. I like to think of this as a nicely framed picture. Okay? You've got the frame around the picture. Maybe that g is like that matting strip that goes around the picture to make it look fancy. And then that's your actual picture that gets put in the middle. Okay? So that's the type of mindset that we should have when we're going through this. Okay? The other thing that I want to point out is composition of functions is not commutative, meaning that the order does matter. Now that doesn't mean you'll never get the same result, but you're not guaranteed to have the same result. So if let's say you do this problem here, and then they ask you to do this problem here, don't think to yourself, well, I already did that, I'm just going to copy that over. It's a different problem. You may get the same result, but maybe not. So let's see how this works out. So I'm going to start with g, which is 3x minus 8. Then I'm going to go this way. I'm going to plug in that f of x, which is 7x plus 2. Okay, let's see how this works out. I get 21x plus 6 minus 8, or 21x minus 2. Very different result. Okay, so again, composition is not commutative. Very easy thing to do, but don't always assume that, oh, if I did this, that's the same result. Okay, because it could be very, very different. The last thing I want to talk about is when we build our own composition. Let's look at a few examples of that. So let's say I give you a function like that. And I ask you to break it up into two components that when we use composition to bring them together, we get that result. Right now we're just kind of messing around with that, that skill. But later on when you get into like a calculus setting, we're going to want to break things down into smaller components. Because sometimes when we do differentiation and integration, it's going to be a lot easier to handle smaller pieces and then, multiple steps versus one big complicated chunk. So how are we going to do that? So it's going to state this. Find f of x and g of x so that h of x equals f composed with g. Okay, and the order matters here, remember. So we want to find two functions so that when I compose them together, I get back to this. So I'm looking to define these. Okay, now think back to that picture idea. This is the frame, this is the matting that goes in the frame, and then this is your ultimate input. Okay? So I like to think, and I always ask myself, what is the big picture here? What is the all-encompassing framework on this expression? In this case, the big all-encompassing framework is that square root. So what I'm doing first, and listen to how I say this, is taking the square root of something. That x is just a blank spot. But what is that something? 3x plus 2. Notice I said x here. Here I just said something. So what am I doing with this? I'm taking the square root of something. That x just is a filler. But then what's that something? The 3x plus 2. It's as simple as that. If it requires too much complexity and creativity to make this happen, a lot of times we're not doing this. Okay. Right now we're trying to get very broad setups and broad situations. So let's look at another one. So same basic concept. Let's say we have something like that. What is the big idea in this problem? Well, I'm taking something and I'm cubing it. What am I cubing? 2x plus 7. Okay, let's do one more. Now this one, again, it's risky to get too creative with this. Okay, because again, the more creative you get, the more complex these get, you're defeating the purpose. What we're trying to do is keep these as simple as possible so that we don't have to deal with something so complex. There is literally an infinite number of possibilities you can use out of these two to build that. But the more creative we get, again, the more complex it gets, and you're defeating the purpose. Okay, so in this case, what do we have going on here? Well, we have that fraction, right? Now the problem is we have an 8, and then we have that 5x plus 3. We can't pull all of those together, okay, because otherwise then we're not really doing anything with this. We're not breaking it down. So let's think of it this way. I have a fraction that has a nice clean 8 on top and something on the bottom. That's a much simpler expression. And now what's that something? 5x plus 3. Okay, I see a lot of people wanting to break that 8 up. And again, when you do that, that's not wrong, but sometimes you're risking making too much of a complex fraction to begin with. We're trying to simplify this a little bit. This is much easier to integrate, differentiate whatever you're doing in the future. Okay, and then this is a piece of cake. So again, when we're doing this, always try to make this as simple as possible. Now, another way they will present a situation like this is they'll give you some options to play out in the very beginning. Let's look at an example of that. So let's say I give you 3 functions. Okay, so, and then they're going to say, build this, okay? So again, it's still that building a composition, but we're not making them up on our own. Here they're saying, use 2 of these, compose 2 of these to make this happen. Now the thing I like to always do is eliminate the one that doesn't fit. In this case, the absolute value of x plus 5 has nothing to do with multiplying something by 2. So f is out. So what it comes down to is a question of, do we have g composed with h or h composed with g? Because remember, those are 2 different outcomes. Now you could just do these 2 compositions and see which one works, or think of that framework idea. What's the big, all-encompassing idea here? We've got that absolute value holding it all together. That's your frame. So the absolute value is h. So we should be starting with h, and then what do we put into h? The x plus 5. So we start with h, and then we plug in g. So what we would be looking for is that. And if we did that composition to check, it would be absolute value of something for h, and then x plus 5 goes inside. If we did this one, just for the sake of discussion, we would start with g, which would be that, and then we would plug in the absolute value of x. And that's not what we were looking for. Okay, so again, if you need to do the two compositions, go right ahead. But if you just think about that framework concept, you'll be able to see the result, which result you're looking for. Let's do one more. Same three functions, but let's say we have that, okay? So I've got that function 2x plus 5. Which of these has nothing to do with it? I would say h. There's no absolute value anywhere, so we're just eliminating that. So the question comes down to, is it f composed with g or g composed with f? Okay? Again, you can do both of them, or what is the big framework here? What's that thing holding it all together? Okay? We don't have a quantity here holding that together, so I wouldn't say the times 2. What about the plus 5? What if we take something plus 5, and then in there we plug in that 2x? If we think of it that way, then that big idea would be the g and then composed with the f. So that would be that right there. And again, just to run through it again, g is something plus 5, f goes in there, which is 2x, and that's what we're looking for. Okay, if we went with this, f is 2x, and then g goes in there, and after we distribute that 2, we would have something different. Okay, so that is pretty much it. We had the algebra of functions, which really is just polynomial, add, subtract, multiply, divide. And then we have the composition. Composition is basically you plug a function into another function. Or we plug a value into a function, the output of that becomes the input into something else, and then we get an ultimate answer. Algebraically, though, I like to think of composition as a frame, the matting, and then the picture. Okay, and again, the matting, if you look at a fancy picture, you have that colored light, or sometimes it's just white, kind of strip around it. That's what matting is. So we have the frame, the wood frame, that matting strip around it, and then the picture itself. Okay, so just make sure you're very clear with your parentheses, careful with your distribution and your negatives, and you'll do just fine. As always, work hard. Let me know if you have any questions. I'll see you next time.